In the previous videos, you saw that if we apply a 10 mV peak-to-peak sine wave to the gate terminal of a MOSFET, the drain current will remain zero. That's because when the input sine wave is at its maximum 5 mV peak, this voltage is still far below the threshold voltage of the MOSFET. So the transistor remains in the cutoff region. That's why we bias transistors. Now if we superimpose the 10 mV peak-to-peak sine wave to the MOSFET that is already biased to work in the saturation region, the fluctuations of the sine wave will be applied to the operating point of the transistor. So when the sine wave is at maximum positive 5 mV, the gate source voltage is VGSQ plus 5 mV. And when the sine wave is at maximum minus 5 mV, the gate source voltage is VGSQ minus 5 mV. Since the drain current in a MOSFET has a quadratic relationship with the gate source voltage, a very small change at the input or the gate source voltage will create a bigger change at the output. This is how we amplify small signals by using field effect transistors. Let's see what happens if we increase the amplitude of the input sine wave. When we increase the amplitude of the input sine wave, the output is amplified further, but the shape of the output wave will no longer be similar to a sine wave. This is due to the nonlinear shape of the drain current. So to amplify signals, their amplitude should be small enough so that the drain current can be approximated with a linear graph or a linear equation around the operating point. Let's see what signals are considered small signals when dealing with MOSFETs. We have a MOSFET which is biased with a constant VGS voltage that is applied to the gate of the transistor. Let's also apply an AC signal VGS to the gate. So the total gate-to-source voltage is the sum of these AC and DC voltages. This is the equation of the drain current in the saturation region. By applying AC and DC voltages to the gate, the drain current will also consist of AC and DC components. Let's expand this equation. The first term of this equation is the DC bias drain current IDQ. The second term is proportional to the input AC signal, and the third term is proportional to the square of the input AC signal. This represents the nonlinear current component, which is considered undesirable. To minimize the nonlinear distortion that is created by the nonlinear current component, this nonlinear component should be kept much smaller than the linear term. In this case, we can ignore its undesirable effect. Similar to bipolar junction transistors, if we use the factor of 10, the small signal has to be less than 1/5 of the overdrive voltage to satisfy this inequality. This is the small signal condition in MOSFETs. In other words, if the amplitude of the input AC signal is smaller than 1/5 of the overdrive voltage, we can achieve a pretty undistorted amplification. If you look at the IV characteristics of an N-channel MOSFET, you'll see that we can bias the transistor at different points. At each of these points, the slope of the curve is different. Let's compare points A and B. Since the slope of the curve is higher at point B, for the same input AC voltage, we'll get a higher output voltage or a higher amplification. Does it mean that we always bias all transistors at points with the highest possible slope? The answer is no. When we bias this transistor at point B, we'll get a higher amplification, but at the same time, the DC bias current is higher, which means that the circuit consumes more power compared to the case when it is biased at point A. So the requirements of the design will dictate the best possible point to bias the transistor. If you want to bias your transistor for a low power application, you may prefer to sacrifice amplification for better power consumption. In the next video, I'll show you how to create the small signal model of a MOSFET.